Okay, so this is an example of what an electric motor is, and how you get a force on it to spin it around and around and around and around. We cut off the last of three-phase motor to get more power, but in general, you get a maximum torque when it's a line in this direction, when the area vector is perpendicular by 90. When the area vector is in the same direction, there's actually no net torque on it. As we spin the other way, you're going to find out there's a negative. If the current's still going in the same direction on the loop, there's a negative torque on it to slow the thing down. Alrighty, let's go on to the next slide here. Oh, so we talked about probably that there's a magnetic field associated with this, and that as the current goes around, it makes a net north pole on the thing, which is going to be one of our last rules for the right-hand rule, to find quickly and easily where the north and south pole is. Okay, so more on that coming up here in just a moment. So just as you have a spin of an electron, if it spins in one direction, you have a net pole. Sure, it's an electron, so maybe I should use my left hand. Well, that'd be fine. That's where the north pole is. So we have a net pole on the thing, and loops can also have that same net pole on there, is where we're getting in a little bit. Oh, so a quick note about nuclear magnetic resonance imaging. So what they're doing is putting you in a giant magnet, and what they're doing is they're lining up your atoms. And they're looking about what the tissue is like by how long it takes when they shut off the magnet. How long does it take for this to go back to the normal direction that everything was going in? And that's how they can look at your soft tissue and see if it's what's going on with your soft tissues by the time it takes these things to relax after they take the giant magnet off. Alrighty, so here we go. Hey, it's an ACT question maybe, huh? Or that's not an ACT question. But so a question is going to be, the current goes this way. Hey, what direction is the net torque on the thing? Well, start up your right-hand rules. So you can use the original one, really the only one I've actually taught so far, is the one if I start right over here on this side over there, the magnetic field is in that direction. Current is up, so the force is into the page there. Okay? Then there's going to be on the top, there's no net force there. Then back over here, the current's going downward, and that would mean then it's pushed down into the page in that case and spins around. But I think this question's going to be, which direction is the thing going to spin? Well, they're probably going to, well, let me see what the question is first. Compare the torque, oh, that's all they're doing. Torque on loop 1 comparing to loop 2, which have identical area and current. So if we compare the two, which of those is the greater torque? Give you a moment. Unpause. Alrighty. So you notice we didn't change the area, right? We didn't change the direction that the current goes in relation to the magnetic field. It goes in a circle like this. So because of that, it turns out it's the very same torque. That's the beauty of just knowing the area, and you don't have to know the shape. As long as you know the area, you're going to get a force in one direction on one side, force on the other in the other direction. And sure, it may not be exactly 90 degrees this loop to that, but because you have a change in direction, it doesn't really matter. You're still going to have the same torque about this axis right over here, just as you do over here, just because you're going to have the exact same area. So that's the beauty of not trying to use a length of this to find the torque, but just knowing the area makes it a lot easier. Alrighty, so finally we're coming out to our next right-hand rule. Wow, there's a lot of stuff on this page. It's called Ampere's law. It's how they say it in French, maybe. I really don't know French. But any straight wire has a magnetic field because you have a moving charge. You shut off the charge, there's no magnetic field. And you can find the magnetic field by these parameters. As you could guess, the more charge you have flowing per second, or the greater current, the greater the magnetic field, because it's going faster. Because remember, that's the QV thing for forces on a charged particle. So yeah, the faster they move, which is a higher current, the greater the magnetic field. Now, in electric fields, we have this thing called the permittivity, a little e thing, permittivity of free space. With magnetic fields, we don't have permittivity, we have permeability. So this is the permeability of free space. So the free space being a vacuum or pretty much air at atmospheric pressure acts about the same. So it's 4 pi times 10 to the negative 7th Tesla meters per amp. Is how we define with that permeability. It's a constant. And in most cases, you're just going to be in the air, probably not in a vacuum in most cases. But that's what we're going to use. So this is what Ampere found, is that you get further away from this thing, the magnetic field gets smaller. So pop quiz, what if you get twice as far away? What happens to the magnetic field? Twice as far away doesn't change the current, doesn't change the permeability, doesn't change the 2 pi, it changes the R. So 2R means, wait for it, half the field. So remember, this is a wire like a cylinder. We had the same exact rule in Gauss's law for a cylinder. And if you have a cylinder, you get twice as far away from the cylinder, you have half the field. You get 3 times further away, you have a third of the field. It's not right with the square of this, because it's not a sphere. It's not the magnetic field away from a sphere, it's for a long wire. So anytime you want to talk about the magnetic field around a wire, it's this specific one, not anything that charge it moves. This is the magnetic field that wraps around a wire. And as you get twice as far away, it's half the magnetic field, and so forth. So that's to find the magnitude of that thing. What about finding the direction? Well, there's a quick and easy way, and this is their right-hand rule number 2. I don't like it, but it still works. So in this right-hand rule, you put your thumb of the right hand along the current. So wherever the current's it's going right at you, out of the page. And fingers of the right hand go along the R, the radius of the thing. As you get twice as far out, it's half the field. But the field will still be in the same direction. It'll just be half the amount that it is halfway in. And it's out of the palms is the magnetic field. That's not the one I grew up with. The one I grew up with I like better just because I grew up with it. And there's a lot of right-hand rules. To me, a better version is to wrap your fingers around the wire to show the direction of the field. So if you can imagine, okay, the field's coming right at me, okay? The field is coming right at me because this is the wire. This is the wire coming right at me, so I put my thumb in that direction. Well, all I'm going to do is wrap my hand around it like this. So it's coming right at my face. I know you can't see it because it's out of order if I go into the where it's like this, but it wraps the other direction now. So by using this, it tells you the exact direction of the field. On top it points this way, on the side it points that way, and the bottom it points that way, and then on the inside it points straight up again. But the field is actually circular. There's no start and end of this field. It's not like an electric charge has a starting and an ending on the electric fields. These magnetic fields, in these cases for a wire, you don't have a start and end. They just go in a circle. But they point in a vector direction. It goes around like this. That's the red version. That's my version of this thing. Now, if you like, you could slip on over to this thing over here. And there's a whole, what do you call that thing? Physics aviary thing on it. And you could examine what the field is like on this. If I wasn't downloading another video while I'm doing this, it would probably come up a whole lot faster. So I'm going to pause just for a moment so I don't waste all my video for this thing to pop up. I didn't get the thing to pop up, but you can look at it at your leisure. It's one of the things I had selected earlier. Just you can look at the size of the magnetic field as it goes around the wire. Okay, so there are several different versions of the right-hand rule, the HR. All right. So in this case, they're showing you the same thing. As the hand circulates around in a circle, it's just showing you how the magnetic field spins. And as you get twice as far away, according to this, it's half the field. Okay, but I prefer the curling of the hands around that, because to me, when you curl your fingers around this thing, it shows you the exact direction of it. Alrighty, so now we have a long wire. The current runs this way. So you can imagine what the fields are like from this wire. And if this charge is moving, it makes its own magnetic field. So remember, this is a moving charge that's in the stationary magnetic field of the line. And I say stationary field assuming the current stays constant. So if the current stays constant, I do the right-hand rule I just learned. I'm going to wrap my hand around that wire. It goes this way. On the back side, it points up. Towards your side, it points down around the wire. So if we're looking at right over the top of that wire, well, that magnetic field from the wire at this first Q over here is actually pointing right at your face. Below the wire, it's into the page or into the screen, but where that Q is, the field is actually coming at you right out in your face. So that's one magnetic field. So I'm saying this stays constant. Well, this also has a magnetic field. Okay, so the question is, compare now the magnetic force on Q in A versus the B. Take a moment, pause, Unpause. So which of those has a larger force? The answer, it is the same. You might say, Dios mío, how is that? Well, remember the direction of the force, where the Q is in both cases? It's right at you. It's coming right at your face. They're both in the same magnetic field, and the direction to this is still perpendicular to the one coming right at you, right in the face. This is perpendicular. They're both 90 degrees. So because of that, they have the exact same force on them no matter what direction this thing's going in the plane of this screen. It could be going this way, this way, this way, this way, or that way, that way. At this point, it's still perpendicular to the magnetic field. You're at maximum force on this thing. Now, as this thing moves, different story, because you're getting further away from the wire, which is a smaller magnetic field, then it will undergo a smaller force. But remember, you're looking at the force on this charge. That's the first right-hand rule. It's the velocity across the field, and in both cases, they are perpendicular to each other. It's the exact same field there. So the magnetic field is coming out at those points in both cases, and it's the same distance, so it's the exact same magnetic field, external magnetic field for both on those charges are moving through, therefore the same force. Okay. So if you wanted to find the net force of this thing, well, that's the first right-hand rule, that the field's coming out, and the velocity is this way. It's a downward force. Now, there's another thing you might note is the directions where we're going with this thing, the directions of the field. So the field's coming out on this thing. Well, if the charge is moving that way, so this is the direction of the magnetic field on the wire. Well, if the charge is going this way, it actually has a magnetic field at the same point going into the screen at that point. They're opposite magnetic fields, hence the attraction there. And we get the same idea over here. The force is in a different direction because the force is perpendicular to that velocity. Okay, so it doesn't matter what direction to go, the force will be perpendicular. Since these are the velocity and magnetic field are perpendicular, that'll be perpendicular to those. But at this point, it is the exact same amount. Okay, alrighty. So we have the same angle to the velocity versus the field, and that's why it's the same force. Okay, alrighty. So now we're talking about wires here. We just have a few minutes left. We're going to go into a third video on this, it looks like. So what two long wires carry the opposite current? What is the direction of the magnetic field above there? Pause for a moment. And when you're unpaused, let's take a look at forces. So let's look at the magnetic field from each of these. Okay, so at this point, which way is the magnetic field going? So if you're not sure, let's use our second right-hand rule, which is the thumb going into the screen, and then that wraps around. So that's a clockwise magnetic field around the X. And what that means is that there's going to be, if that depends on what kind of charge that is, I guess they're not really telling us what kind of charge it is, but so they're using a direction of the magnetic field as it goes around in a circle. The field at that direction still goes clockwise, so it's still that strong. Now this is the same distance away, but remember it's going inward. Because it's going inward, we've got the magnetic field that wraps at that point down and around. So since that's going downward, oops, I'm sorry, I had my thumb in the wrong direction. It's coming out at you, not inward. The X was the inward. This is coming right at you. That means the field is in that direction at that point. Okay, so the field is going like curving like this. So what do these two do to each other? Well, they don't cancel out. Only the X components cancel out. You have a net Y component, right? Since the X components cancel out, there is a net Y magnetic field that points in the B direction, which is the upright over there. Okay, so now let's look at currents and forces on wires that are in the same and opposite directions. Okay, I'm going to pause right here because I'm not going to be able to finish. I just have a few seconds left, and I'm going to pick up here, and we're almost finished here. All right, and we'll talk about so in the meantime, figure out which of these are going to attract, which are going to repel, or are they going to be neither of the above before we hit our last video.